Probability distributions. What is a random variable? So a random variable can take on any of the values with equal chance, or whatever the chance is of that. So when we're rolling a six-sided die, well, each of those 1, 2, 3, 4, 5, or 6 are possible, and they each have the equal amount of chance. Discrete random variable is when there's a list of possibilities. So when we roll a dice, you can't roll a 1.5 or 1.75. Discrete means that it's countable and there's a certain number that are there. So there's a little example there. Number of threes obtained when rolling a dice 4 times. How many threes could you get? You could get 0. You could roll a dice 4 times and never get a 3. You could be extremely lucky if you were really wanting 3s and get 3s all 4 times. So if we wanted to say what are the total number of possibilities, you could get 0 3s, 1 3, 2 3s, 3 3s, or 4 3s if you conducted that experiment 4 times. A continuous random variable is when all possibilities in a certain range could happen. So in the second example there, if you're having a car race, there's an infinite amount of possibilities, because you could go to the, I don't know how accurate they are in measuring times now, but they could go to the millisecond or the microsecond or whatever, and every single time possibility is there. What we look at in a probability distribution for discrete random variables is a list of each of the possibilities and then the probability or chance of each of those things happening. So we start off with something simple. Suppose you toss a coin twice. What's the sample space in a tree diagram? Well, first of all, what could happen? You could get, on your first throw, a heads or a tails. And then you throw it a second time, and you could get heads or tails. So our sample space, you could get 2 heads, a heads and then a tail and then a heads, or 2 tails. What we can do with this data is create a probability distribution. So the way the probability distribution is you pick one of your variables to be, in this case, the number of heads obtained. If you toss a coin 3 times, there's 3 possibilities. You could get 0 heads, you could get 1 head, or you could get 2 heads when you do that. In a probability distribution, we write, what's the probability x equals x? What were our chances if we look at our sample space? There was 4 possibilities. What were the chances of getting 0 heads? Well, that was 1 out of the 4. How many had 1 head? There was 2 of them, the heads then tails, or the tails then heads. So we would say the chances of this is 2 out of 4. And getting both of them, whoops, that is terrible. Thinking about 2s. Getting both of them heads, well, there was 1 that had both of them heads. We call this a probability distribution chart. It describes an event, and this time the event was the number of heads that you could get. Along the top, we write out all the possibilities. So when you toss a coin 2 times, you could get 0 heads, you could get 1 head, or you could get 2 heads. And then underneath, we write the probabilities of each one. This part here always adds up to 1 because it's looking at all the possibilities. And so it has to add up to 100% in the end. So this says the same thing. For any random variable x, the probability of that event has to be somewhere between 0 and 1. You can't have something with a probability of over 100%. And if you add up all those probabilities, remember that this symbol means the sum. If you add up all the probabilities along the bottom, it will always equal 1. So I've already done the tree diagram there for tossing a coin 3 times. And if we now think, what are the chances of getting the number of heads? There would be 4 possibilities. So in this example, when making our probability distribution chart, and x represents the number of heads, you have a possibility of getting 0 heads. We have a possibility of getting 1, of getting 2, and of getting 3. So the first thing we have to understand is that those numbers across the top. We flipped a coin 3 times, and we're just listing all the possibilities of the number of heads that we could get. Starting with the smallest value, you could get 0 heads, and then up to the biggest value, you could get 3. Then looking at the probability here, how many have 0 heads? Well, there's only the one that has all tails. That's 1 out of 8. How many have 1 head? 1, 2, 3 of them. 2 heads, also 3 out of 8. And 1 head, 1 out of 8. Notice us flipping a coin twice and the tree diagram compared to flipping the coin 3 times and the tree diagram. Okay? For homework, why would it be mean to say, draw the tree diagram if you flip a coin 100 times? It would be a huge tree diagram. So our initial stuff that we've started here is going to run into problems later on if we get too big, right? And that's often a mathematical type of problem, saying, good, your method works in simple situations, but your method doesn't work well in bigger situations. So we're going to be leaning towards, well, how could we do things when things get big? The box contains 2 red marbles and 6 green marbles. Two marbles are chosen at random with replacement. So what that means is you choose a marble, look at it, note its color, put it back. Choose another marble, look at it, note its color, put it back. So when choosing your first marble, you could either get a red or a green one. Our probability, since there's 8 marbles in total, the red is 2 out of 8. The green is 6 out of 8. You choose your second marble after replacing it. Could get red or green again. Again, it's still 2 out of 8 and 6 out of 8. 2 out of 8 and 6 out of 8 because the marble was replaced. We're letting x be the number of green marbles. So it is possible that you didn't pull out any green marbles. It is possible that you pulled out 1 green marble, and it's possible you pulled out 2 green marbles. This time, though, the probability isn't just based on the total number of things in the sample space. Because the red-red possibility is going to be, well, 2 out of 8 times 2 out of 8. Are you okay if I reduce those to 1 over 4 and then multiply them to get 1 over 16? Yeah? So I took both of those fractions, reduced them, to 1 over 4. 1 over 4 times 1 over 4 would be 1 over 16. The next two branches, 1 over 4 times 3 over 4. So red-green's probability, I guess I should write this proper notation here, probability of red-green would be 3 out of 16. The probability of green-red would also be 3 out of 16. And the probability of green and then green is going to be 9 out of 16. A quick mental math thing that I did at the end there, just to check to make sure everything was right, is I added those up. Do they add up to 100%? They do. And now I can fill in my chart. Which one represents 0 green marbles? Red, red. So that'll be 1 out of 16 chance. 1, there's two cases for 1, so you could add them up. I'm going to keep it out of 16, but you could reduce that to 3 out of 8 if you'd like. And finally, green, green, 9 out of 16. Example 6, we're getting a little bit more complicated here. We're rolling 2 dice. It says draw the sample space as a lattice diagram. That's just your big chart of all your dice. But now we're figuring out the difference between the higher one and the lower one. How long would it take to play Monopoly if you did it this way? Well, I don't know. You just wouldn't get around the board very fast. You'd run out of money in the first round. It'd be kind of interesting. Plus, it would really suck if someone owned Boardwalk and had hotels, and you kept rolling 0 to stay on it over and over and over again. So from this, we can set up all the possibilities of what you could roll. You could just roll a 0, a 1, a 2, a 3, a 4, or a 5. And there are the probabilities of each one. Once again, they would add up to 1. All right. First one, this is not a probability distribution. How come? Because it doesn't add up to 1. Question number 8. There's your probability distribution chart. And we can put in the probabilities even though we don't know what they are. But since they have to add up to 1, you can calculate that A has to be 1/6. Yes. All right. I can go back to any of these in the end if you'd like. There's our tree diagram for example 9. 3 possibilities. X is the number of white cubes, so you could get 0, 1, or 2. And you could reduce those fractions if you wanted to, or you could leave them like that. The nice thing about reducing them is it makes the mental math easier in some places, right? Like 1/2 is easier than multiplying by 4/8. The nice thing about not reducing them is when adding these up to check if they equal 1, they all have a common denominator if you don't reduce them. And the last one, I have J for job and J for non-job. X denotes the number of successful applicants. So we could have both of them non-successful, or both of them successful, or just one getting the job. Yes. It doesn't matter if you change them to fractions. In fact, fractions would probably be easier mental math-wise to work through it. Okay? It's an interesting time. When does that happen? Because if I would have asked you in grade 7 or grade 8 if you liked fractions or decimals better, you would most likely have said decimals. And then somewhere along the line you realize that, oh, doing math with fractions is actually easier.